Almost everyone knows that it is impossible for anything to move faster than light. This speed, 300,000 kilometers per second, is like the universal speed limit. What most people don't know is that a lot of mind-blowing stuff happens when you get really close. You can call me the Professor, and this is my assistant.
Appreciate it, Doc.
Today we are going to discuss special relativity. This theory, proposed by Einstein himself, tells us how time and space are intertwined. It also shows us exactly what happens as you approach the speed of light. There are two main postulates of special relativity. You just have to take my word for it that these are true, but from these we can derive everything else. The first is the principle of relativity, which simply states that the laws of nature are the same in all reference frames. The second is the principle of invariant light speed, which tells us that the speed of light is the same in any reference frame. Now, to get from these ideas to the strange effects of relativity, we're going to have to do a few thought experiments. Let's get started. Imagine a fast-moving train going along a track at a constant velocity. On the back is our experiment setup. It consists of just a laser and a mounted mirror. The laser shoots a beam of light. It bounces off of the mirror and returns to the laser, all at the speed of light. Simple, right? Now let's look at the same scenario from a different reference frame, like a person watching the train go by. From this perspective, the laser moves in a diagonal path due to the train's movement. Let's look at these two situations at the same time. Keep in mind, these are the exact same event, just seen from different frames of reference. In one, the light moves in a straight up and down path. In the other, it moves in a longer, triangular path. But remember, light moves the same speed in any reference frame. The second beam must travel a greater distance, but at the exact same speed, so it will take more time to do so. That means the same event takes longer to occur in the non-moving reference frame. Time itself has slowed down. We call this phenomenon time dilation. Now, with a little math, we can come up with a pretty simple equation relating the passage of time in both frames. Delta t prime, the amount of time passed in the moving frame, is equal to delta t, the time in the static frame, multiplied by the Lorentz factor, gamma. Gamma is just 1 divided by the square root of 1 minus v divided by c squared, where v is the speed of the object and c is the speed of light. We can also derive a similar equation that relates to lengths. You see, when an object travels at high velocities, it gets squished along the direction it is moving. This is called length contraction. Again, the primed variable corresponds to the moving frame. This will be very important later, but for now, let's focus on time dilation. We have outsourced this thought experiment to a specialized department, also known as this guy. Here, we see this truck at rest on an infinite straight road. To him, all the other vehicles are driving at precisely the speed they're supposed to be driving at, regardless of whether or not it is safe. Now, let's set the truck moving. Here we have a driver's view of the situation. We are now traveling at 30 meters per second. Notice how absolutely nothing has slowed down. This is because the time dilation effect is completely unnoticeable at such a cosmically low speed. Let us attempt to force it into action. Now, we'll accelerate the vehicle to 10,000 meters per second, the fastest speed ever reached by a human being. In the other direction. Now, in order to contain this massive speed, we have had to change the course a small bit. There were some issues. It might have been hard to spot, but despite this incredible speed, there is still no perceivable difference between standing at rest and moving at 10,000 feet per second for the observer. This is because 10,000 meters per second is still nearly 4 orders of magnitude below the speed of light. Our outsourced department, however, assures us that it has acquired the means to install a black magic accelerator to the truck. This should allow us to observe something remarkable. This will accelerate the truck to 2.99 times 10 to the 8th meters per second. This will cause a dramatic shift in the way the truck driver sees the world. He will not see himself moving through it, instead he will see the world moving around him. Or perhaps our outsourced department has misled us. However, this is still an adequate representation of what it should look like. Now, let us go to the physical proof of this theory. Proving that relativistic effects are real is a bit tricky. We just showed that we can't build anything that goes anywhere near fast enough to see any effect. But while we can't reach those speeds, we know something that can. Muons. Muons are elementary particles similar to electrons that can move at incredible speeds. They are naturally formed when cosmic rays react with the atoms in the atmosphere. They shoot off at high velocities, but because of their short lifetimes, they should only travel at most 1,000 meters before decaying. However, since the muons are moving at near the speed of light, they experience time dilation and are easily able to make it to the surface. Muons can be observed in a lab using tools like a cloud chamber. The particles leave a trail in the gas as it travels through. Since we can see these muons on the surface, and they certainly can't go faster than light, time dilation must exist. Now that we have a firm understanding of the theory behind special relativity, let's talk about something more fun: space travel. One of the biggest hurdles with theoretical space travel is the immense distance between stars and the time it takes to move between them. Using relativity, we can sort of get around this problem. Let's get to work.
Oh!
In order to have a good comparison, I've cloned our little friend.
Cream gravy.
This one will stay here on Earth.
Alrighty then.
Now then, let's start in the reference frame of someone on Earth. From their perspective, the rocket flies off towards planet Genz at 0.999 times the speed of light. Length contraction and time dilation do have an effect, but it doesn't change our result. Time dilation causes the engineer inside the rocket to move in slow motion, while length contraction causes the rocket to squish together in the direction of travel. Genz is about 25 light years away, so it would take around 50 years for a round trip. Now let's look at it from the rocket's perspective. In this reference frame, it is not the rocket that is moving, but the universe around it. That means that length contraction shrinks the whole universe instead, causing the planets to come closer together. From the moving rocket's perspective, they are actually only about 1 light year apart, so the whole trip only takes 2 years. Amazing! The engineer was able to travel 50 light years total, and from his point of view, it only took 2 years. But before you get your hopes up, we did not just unlock the secret to long-distance travel. There is still a major flaw in this design. Remember, while the trip only took 2 years from the rocket's frame, it took 50 years in the Earth frame. The red engineer actually aged less. The clone is now 48 years older than the original. So while you can abuse relativity to travel across the galaxy, don't expect humanity to still be here when you get back. Well, that's all the time we have for today. See you next time.